everyone. I am Dr. Manisha Verma from Acharya Narendra Dev College. Recently I have started a lecture series on thermal physics in which I have already discussed many important topics pertaining to thermal physics. Recently I have started with discussion on thermodynamic potentials. Today is my 7th lecture in the series on thermodynamic potentials. In the last lecture, I had derived the Clausius-Clapeyron equation. What is the Clausius-Clapeyron equation? How it can be derived? What are its applications? What is its importance? In continuation of my last lecture, I move on to one very important application of the Clausius-Clapeyron equation, namely the existence of the triple point. So what is the triple point? The triple point of any substance is the temperature and pressure at which the three phases in which that substance may exist, gas, gaseous phase, liquid phase, solid phase, and at the triple point what happens is that the three phases coexist in thermodynamic equilibrium. The single combination of pressure and temperature at which pure water, pure ice and pure water vapor can coexist in a stable equilibrium occurs at exactly 273.16 Kelvin and a pressure of 611.73 pascals. So you can see and appreciate that the triple point of water can be used to define the Kelvin scale of temperature. The triple point temperature of mercury is at minus 38.8344 degrees Celsius and the pressure at the triple point is 0.2 millipascals. So you can see that the triple point for different substances is different and is unique to that substance. Now what is the significance of the triple point? At the triple point, it is possible to change all of the substance to ice, water or vapor by making very small changes in pressure and temperature. So this figure is showing the triple point in the case of water, and you can very well see the three lines are representing the phases boundary, and you can see the solid liquid boundary has a negative slope. So on the left hand side of the solid liquid boundary you have the solid, and on the right hand side you have the liquid, and at the point T is called the triple point. And you can see that this graph is the PT graph, that is pressure is plotted versus temperature. Pressure is taken along the y-axis and the temperature is taken along the x-axis. Just explaining the graph further, we can see please see the line TC. The line TC. Now let me explain what this line means. The line TC gives the vapor pressure of liquid water up to the critical point C. Along this line, liquid and vapor coexist in equilibrium. At temperatures higher than that of point C, the condensation does not occur at any pressure. So along this line, we mean that at one side of the line we have the liquid phase, and on the other side of the line we have the vapor phase. Now let us understand the significance of line TA. The line TA gives the melting point of ice and liquid water. The plot shows the temperatures and pressures at which ice and liquid water are in equilibrium. Note that at the dashed line TD, liquid water can be cooled below the freezing point to give supercooled water. Again I am showing you the graph for a better understanding. This explanation shows that the two phases are in equilibrium along the three solid lines, but when these lines intersect at one point C, the three phases coexist in equilibrium. This intersection is the triple point where a substance may simultaneously undergo the processes of melting, evaporation and sublimation. So this was as far as the applications based on the thermodynamic potentials and the Maxwell relations are concerned. Now, because Clausius-Clapeyron is a very important concept in physics, especially in thermal physics, let me just briefly tell you and discuss certain problems based on Clausius-Clapeyron equation, how to apply Clausius-Clapeyron equation, and how we can find out the depression in the melting point or in the boiling point with respect to pressure. So let me discuss the first problem. What does the first problem say? The first problem says that calculate the change in boiling point of water by taking the normal boiling point as 100 degrees Celsius with the latent heat of vaporization as 2.26 into 10 to the power 6 joules per kg, specific volume of water 1 meter cube and that of steam is 2.676 meter cube, and change in the pressure is 1 atmosphere, where 1 atmosphere in terms of Newton per meter square is 1.015 into 10 to the power 5 Newton per meter square. So therefore, what are we supposed to find out? We are supposed to find out the change in the boiling point, that is dT. Okay? Normal boiling point is given as 100 degrees Celsius. Latent heat of vaporization is given as 2.26 into 10 to the power 6 joules per kg. V1 is given as 1 meter cube, V2 is given as 2.676 meter cube, and dP is given to be 1 atmosphere, which we can write in terms of Newton per meter square. So from Clausius-Clapeyron equation we have dP by dt is equal to L by T V2 minus V1. We are supposed to find out dt. So dt is T V2 minus V1 by L into dP. So this means which will give us is equal to 27.97 degrees Celsius if we substitute all the parameters. Here the transition is from water to steam, therefore V1 is taken as 1 meter cube, V2 is taken as 2.676 meter cube, dt 1 temperature is given 373 Kelvin, we are supposed to find out T2, and L is also given, dP is also given. If we substitute all the parameters here, you can very easily see that dt will be 27.97 degrees Celsius. Next question. Calculate the depression in melting point of water assuming the normal melting point of ice as 0 degrees Celsius, which means 273 Kelvin. The latent heat of ice is given as 3.35 into 10 to the power 5 joules per kg. Specific volume of water is 1 into 10 to the power minus 3 meter cube, and that of ice is 1.091 into 10 to the power minus 3 meter cube, and the change in pressure is 1 atmosphere. So again, from Clausius-Clapeyron equation we have dP by dt is equal to L by T V2 minus V1, or dt is T V2 minus V1 by L into dP. Substituting the various parameters here, we get dt as minus 0.0074 degrees Celsius. Here T is taken as 273 Kelvin because T was 0 degrees centigrade. V1 is 1 into 10 to the power minus 3 meter cube. V2 is 1.091 into 10 to the power minus 3 meter cube. Why do we get a negative sign? Negative sign is taken due to decrease in melting point of ice with increase in pressure. Next question. Mercury melts at minus 40 degrees Celsius at 1 atmospheric pressure. Its density is given by 13590 kg per meter cube. Density of solid mercury is also given 14190 kg per meter cube. Latent heat of fusion is 9786 joules per kg. What would be the melting point of mercury at 800 atmospheres? Now, first step in any question on Clausius-Clapeyron equation, please see the units in which the question is presented. Degrees Celsius has to be converted into Kelvin. So, T is equal to minus 40 degrees Celsius, which will give me 233 Kelvin. dP is P2 minus P1 is equal to 800 minus 1 equals 799 atmosphere is equal to 838 into 10 to the power 5 Newton per meter square. V1 is specific volume given by 1 by 13590 meter cube and V2 is 1 by 14190 meter cube. If we substitute all these parameters into the Clausius-Clapeyron equation, we get dt as 5.916 Kelvin. And the melting point will be minus 40 plus 5.916 is equal to minus 34.08 degrees Celsius. Here the pressure is increasing and the melting point is also increasing as it is mercury. The value of V1 is at 1 atmosphere and V2 at 800 atmospheres. Thus, a positive sign is taken for dt because the melting point is showing an increase which is represented by a positive sign. So, likewise, we can do a number of questions based on the Clausius-Clapeyron equation. Let me do one question based on change in boiling point. Calculate the change in boiling point of water when the pressure is increased by 1 atmosphere. The boiling point of water at the atmospheric pressure is 373 Kelvin. Specific volume of water is 1 meter cube and CV of steam is 1.671 meter cube and the specific latent heat of steam is 2.268 into 10 to the power 6 joules per kg. If we substitute all the parameters, the answer will be 11.04 Kelvin. So, I hope you have understood how to apply the Clausius-Clapeyron equation and how to get the appropriate results. Now, if you remember, in my last lecture I had mentioned that Clausius-Clapeyron equation is an illustration of the first order phase transition. Now, let me move on to the second order phase transition. A phase transition where the second derivative of the Gibbs potential is discontinuous at the transition point, but the first derivative is continuous is called the second order phase transition. In this particular kind of phase transition, no latent heat is required for the transition. And very important examples, if you remember, in the first order phase transition, The examples were simple evaporation, sublimation, melting, but in this case the examples are: first example, lambda transition from liquid helium 1 to liquid helium 2 at the lambda point, where lambda point the temperature is given as 2.19 Kelvin. Now why is this temperature important? Because below this temperature helium becomes helium 2 and above this temperature helium is helium 1. And helium 2 and helium 1 are very different in their properties. Helium 2 displays zero viscosity, helium 1 has viscosity. So this temperature and this phase transition of helium 1 to helium 2 represents the second order phase transition. Another example is the Curie point. What happens at the Curie point? The substance changes from ferromagnetic to paramagnetic substance. Third example is normal metal to superconductor at zero magnetic field. So normal metal changes to superconductor at a particular temperature T equal to Tc, which is called the critical temperature, and this occurs at zero magnetic field. Why zero magnetic field? Because it is the intrinsic property of a superconductor to expel magnetic field. That is what makes a superconductor different from an ideal conductor. An ideal conductor has zero resistance. Superconductor also has a zero resistance, but in addition the superconductor also displays the Meissner effect, which is represented by B equal to 0. As mentioned just in the previous slide, the second order phase transitions have continuous G and its first derivatives, but discontinuous second derivatives as shown in the figure in the next slide. So you can see the slide. G is continuous across Tc, V is continuous across Tc, S is continuous across Tc. Both V and S are first derivatives of G, and Cp is discontinuous at Tc because it is the second derivative of G. So I hope this figure is clear. The first figure is representing G versus T, second is representing the first derivative of G with respect to T, S is also representing the first derivative of G with respect to T, and Cp is representing the second derivative of G with respect to T. So we get a discontinuous Cp but continuous G, V and S. Now let us derive the Ehrenfest equation for the second order phase transitions. Like the Clausius-Clapeyron equation for the first order transitions, the two Ehrenfest equations for dP by dt describes the discontinuities in the second order transitions. These equations connect the discontinuities in Cp and volume coefficient of expansion alpha and are called the Ehrenfest equations. Ehrenfest equations are two in number. The variation of Gibbs potential and its derivatives in second order phase transitions from the equality of entropies in the two phases, while that connecting discontinuities in the isothermal compressibility kappa and alpha is obtained from the equality of volumes in the two phases. So in one case, for the first equation, we equate the entropies, and to derive the second Ehrenfest equations, we equate the volumes of the two phases. So because we are equating two different quantities, we get two different equations called the Ehrenfest equations. Now let us derive these equations. So first of all, I will derive the first Ehrenfest equation, which is a direct outcome for the Cp discontinuity curve, which we have just seen in the previous slides. Let us take entropy to be a function of pressure and temperature. where pressure and temperature are independent variables. Now, entropy does not change in the second order phase transitions, as we just mentioned. So, therefore, if 1 represents phase 1 and 2 represents phase 2, we should be having S1 P comma T is equal to S2 P comma T. This means entropy of phase 1 is equal to entropy of phase 2. Let me take the differential of both the sides. I get ds1 P comma T is equal to ds2 P comma T. Now, let me expand S is equal to SPT, and let me use the very common definition delta S by delta T at constant P is equal to Cp by T. I have used this in a number of times in my previous lectures also. So, what do I get? I get Cp1 by T plus delta S1 by delta P at constant temperature into dP by dt is equal to Cp2 by T plus delta S2 by delta P at constant T into dP by dt. Now, in the previous lectures, we have seen that dG is equal to VdP minus SdT. So, we will use this to derive the first Ehrenfest equation, and how to derive it we will shortly see. I hope you have understood that we have two Ehrenfest equations based on the equality of two different parameters. So, I will continue this in my next lecture.